Hello, class. Welcome to our next worksheet for our industry physics course. What we have here is a complex circuit, but an RC circuit, so a combination of resistors and capacitors. At first glance, what we're looking at is resistor 1 and 2 that are in series, and then between these two nodes, we have three capacitors where they are on two parallel paths, but on path 1, capacitor 1 and 2 are in series, and then this path is parallel with capacitor 3. And we have our secondary path with a switch that will allow current to, as currents being stored here, or charges being stored in the capacitors, it can be flipped and allowing current to then go back to the battery. Really, a switch should be around here, but still. As far as our values, resistor 1 is going to be 130 ohms, resistor 2 will be 266 ohms, and then capacitor 1 will be 5/9, 5/9 farads, capacitor 2 will be 5/2 farads, and capacitor 3 will be 5/9 or 5/9 farads. As far as looking through this worksheet, key here is we are starting with a 40-volt power supply that was connected in the RC circuit outlined above. So now we know that our battery is 40 volts. Question A is going to ask us to simplify the circuit to a single resistor and capacitor, and then sketch that in circuit notation. Question B asks us to determine the time constant in seconds. Tau is just going to be our most simplified resistor, RT, multiplied by our most simplified capacitor, CT. Question C, the switch in the circuit was left open for 80 seconds, allowing the capacitor to charge. At this time, what would be the voltage across the equivalent capacitor? Well, Vc of t, the voltage across the capacitor after a certain amount of time, will equal Vb, the voltage across the battery supply, times 1 minus e raised to the negative t over tau. That should have a negative sign there. Let's see. Okay, the negative sign is there. It's just that it looks like it's part of the denomination sign for the t over tau. But alright, that's good. So 1 minus e raised to the negative t over tau, where t is the amount of time that our capacitor has been storing charge, and tau is the time constant. Question D, how much time would need to pass to charge the equivalent capacitor to 80%? That is 80% of the power supply. Well, that equation will be negative tau times the natural log of 1 minus a, where a is the decimal version of our percentage. So instead of 80%, 0.8. And that will equal the amount of time. And then lastly, question E. Closing the switch in the RC circuit causes the capacitors to discharge. If the equivalent capacitor was charged to 25 volts, so not 40, but it only got charged to the point where the voltage difference was 25, what would be the voltage across CT after 1 hour, or 3,600 seconds? And for that, the voltage across the discharging capacitor after 3,600 seconds would equal VO. The voltage across the capacitor before it is starting to discharge raised to E, or multiplied by E raised to negative t over tau, where again t is the amount of time, in this case time that the capacitor has been discharged, over tau, the time constant? Well, first thing that we can look at is resistor 1 and 2. They are in series, so we can simplify them in one step. As far as our capacitors, C1 and C2 are in series, so we will simplify those first. Then we will simplify C12 and C3 through our parallel formula. What we have here is resistor 1 plus resistor 2, or RT. That would be 130 ohms plus 266 ohms to get 396 ohms of resistance. Capacitors 1 and 2, again, are in series. We have to start there, and because these are capacitors, we'll use our reciprocal formula, where C12 is 1 over C1 plus 1 over C2, and then that sum raised to negative 1. So 1 over 5 ninths becomes 9 fifths. 1 over 5 halves becomes 2 fifths. 5 ninths plus 2 fifths, that would be 11 fifths. And that raised to negative 1 gets us to 5 over 11 farads. And then CT would be C12 plus C3, because now our simplified capacitor C12 is along one path and C3 is on a parallel path. So now we can simplify those using our addition formula for capacitors, where CT equals C12 plus C3. So 5 11s plus 5 ninths, and if we simplify this, 9 times 5, 11 times 5, add those together, that gets us to 100, and then 11 times 9, that equals 99. So 100 over 99 farads. And to draw that, basically just redrawing our entire sketch, but now having our T as our single resistor and CT as our single capacitor. Now that we have that bit of information, the time constant tau will just be our simplified resistor, 396 ohms, multiplied by our simplified capacitor, the capacitance of which equals 100 over 99 farads. And this becomes 400, and an ohm times a farad is a second. So our time constant is 400 seconds. For question C, the voltage across our charging capacitor after 80 seconds, we'll need to use our 40-volt battery supply multiplied by 1 minus E raised to negative 80 seconds that we've been charging the capacitor, negative 80 over 400, 400 being our time constant. And if you plug that into your calculators correctly, you should get 7.25 volts. That will be the voltage across the simplified capacitor. As far as charging our capacitor to 80% of the way, or 80% of our battery supply, well, in this time, we're going to turn, instead of 80%, we'll use 0.8, the decimal version of our percentage. Basically, just divide the percentage by 100%. That's how we'll get A, or divide it by 100. So, according to our equation, time that it takes to charge to a certain percentage is negative the time constant times natural log of 1 minus A. So negative 400 seconds times natural log of 1 minus 0.8. And that will get us about 643.775, so roughly 644 seconds. Lastly, question E. This asks us to calculate the voltage that will be across our simplified capacitor after discharging it for a certain amount of time. And that equation will be VO times E raised to the negative time over tau. VO is the voltage across our capacitor right at the moment that we start discharging it. That could be equal to the battery supply. If you see in your problem that says that the capacitor was fully charged, Basically, that means that we're assuming it was charged so that the voltage difference equals the power supply, VB. But in this case, we were told a different value. We were told that the capacitor was charged such that the voltage difference got up to 25 volts. So we'll use that. And then it was discharged for 3,600 seconds for 1 hour. And the time constant is still 400 seconds multiplied by -1. That will be the exponent of E. And then that quantity times 25 gets us 25 times E raised to -9, or 0.00308 volts. So 25 volts is where we started before the capacitor began discharging, and it made it all the way to 0.00308. So mostly all gone. Capacitors, they can never be fully charged to 100%, and they can never be discharged to 0% because it's more of a logarithmic negative exponential function. In any case, that would be our worksheet for this week on RC circuits. As always, pleasure to have you all in class. For those of you who may not be in this course, if you would like, you're welcome to subscribe to the channel and also like the video just for funsies and to see if this becomes a nice side career. In any case, pleasure to have you all and wish you all the best on your future weeks. Peace.